she is a big supporter of helmet-based ventilation. So, you know, like during COVID, sometimes they were using these plastic helmets. So we had a meeting with her to show our device, and it turns out like Professor Selke was working on an attachment device to measure the pressure and flow, which we actually later brought in Bangladesh. We used that in our clinical trials. But at that time, I didn't know that Professor Selke was behind it, so we talked with some of the students. But now, you know, he's coming and we got connected again. Like, oh, okay, so you're the inventor of PEEP-Alert. We've been using that in Bangladesh. So again, welcome, Professor Selke. Thank you very much.
So anyway, I'm happy to be here, and I was really enjoying seeing the biomedical things you are doing. So many projects, so many capstone projects, and you should be very proud of your work. I'm happy, and you probably saw when I was looking at it, I love to think about these things. But also, it's important when you design things to think about the problem and what you're trying to solve. And I think a lot of the things you were showing are things that maybe you're thinking, okay, how to make it apply to Bangladesh. But I see the quality of the students and the projects you're doing, and we can think bigger. We can think of things that nobody is doing anywhere. And that's always fun, because I like to do things that no one else would have done. Like to do. So my background, I made the pointing device in the Lenovo laptop, and I had a lot to do with making the laptop. Then I left to go to be a professor for 10 years at the Media Lab. And when I was at IBM, I had a group that did physical interface, graphical interface, and cognitive interface. So thinking about all of the aspects of what we have to do to interact with things. So just to give you an example, maybe 1990, early 90s, doing already special input devices for VR, MR, virtual reality. And also some thinking about ways of understanding how to communicate to a person performance problems in even how memory moves through the computer. So this representation here is something I did with visualization. Visualization we used to understand how mistakes, problems that were going on in how memory was allocated for the Power PC. And if you look at this picture, just not to spend time on it, but you notice that this one is a different shape than M and D. This is disk, memory, and TLB. And so the TLB, the shape of the array you are breaking down, just by doing this visualization, you see that there's a difference. And so the algorithm that can make the array that you are multiplying fit into the next level of the memory hierarchy was different. We made a 30 times performance improvement in all vector operations for the Power PC. That year, of course, unfortunately, HP had trouble, and Sun had trouble because we just made software change. So software often is a very big thing. But anyway, many things that I've done, this graphical interface for the ThinkPad, of course the track point, the pointing device, it made a difference, but that graphical interface, it saved about $10 on every laptop by making a very concrete way of understanding things. So maybe I shouldn't talk about user interface, but I care very deeply about ways of presenting things. So I can talk about all sorts of things, but what I want to say is I went to Media Lab to try to explore bigger ideas across bigger industries than just computer. And then I went to Carnegie Mellon and taught for 5 years to build a PhD program in Silicon Valley. But I actually love to help companies. And at MIT Media Lab, we had 130 companies to help. It was a lot of fun. Now I also work with companies. I work with my own companies, and I work with universities. So I'm working at several universities. I teach at a couple of universities. So this is a little bit about me. But what I want to talk about today is what happened in March of 2020. My brother, John, he found this paper, and it says that 30% fewer people die when you have positive pressure helmet than early than if you just use a ventilator when you need to at the end. And already there are people using it in Italy. So we thought, wow, this is so easy, so easy. So I got some money from a philanthropist, a lot of money actually, and we started helping the whole industry make these helmets. It's funny because actually the first time that people used positive pressure to improve people's ability to live was in the 1700s. So there are pictures of a whole room and people sticking out of the room. But this is a early patent up here. Somebody just did a room, and these during the polio epidemic, they made maybe they had thousands of these things you get in Iron Lung, they call it. And here's Iron Lung up here. So positive pressure has been putting pressure on the lung. It's been a good way of getting people to not stop being able to breathe. And during COVID, of course, we have this terrible problem. But the polio and many other indications. In fact, there's a study that we found that said that $500 million a year in the US, that's a lot more here, could be saved just by using these helmets to keep people from getting on ventilator. Once you are on a ventilator is a machine that will give pressure, and then different pressure, and different pressure. If you fight this pressure, you can make gigantic pressure in your lung if you're fighting it. So they put you in a coma. So they have to turn off your brain because it's too difficult to get synchronized with the ventilator. Then if you aren't synchronized with this ventilator, then you can actually hurt your lungs. Then you have to get a lung transplant. A lung transplant is more dangerous than a heart transplant. Very, very bad. So many people in COVID lost their lungs and then they lost their lives. So this is not a small thing, and there are many ways to apply some oxygen, but the pressure with the face mask, it is hard to get enough pressure. And with the cannula, the high flow cannula, the tubes going in your nose, not easy to get pressure at all. And so this idea of putting this bag over your head, it's a very interesting idea. Also, there are many manufacturers, and the best ones, you can tolerate it for weeks without degradation. Some of the helmets that we made more recent in the public, they hurt your necks. But anyway, so this bubble, this helmet is used for decades. Here are some people in Italy. And what's interesting about this helmet over your head is that by having that, you can actually control the air coming out. So if you have disease, then you can stop it. Okay? So in fact, this had a filter on the output, and this I 3D print, and this goes to the helmet. Okay? So this is a N95 filter. So we find that early application. So when you get into, when you start having trouble breathing with the oxygen or with the CPAP, you can get enough pressure so that even in the ambulance you can help. Even in the hallway you can help a person. So these helmets, it's almost like an intensive care unit in one little bag. So it's very good. And then the nurse doesn't get the bag. And so there's a whole lot of studies, and they can sometimes people are in these things for 3 weeks, very long. Now, 3 days, more normal. Many times it's just a few hours. But what happened is this OFRR is an organization that I built with John Selker, Frank Selker, and Mark Johnson. And we got some philanthropy, and we started going, and we got Subsalvit to make a new helmet. We got Omron to make a new helmet. We work with Phoenix. We work with Intersurgical a little bit. They know what they're doing, so they don't really want any help, but they do a good job. Dymar, there's many manufacturers. But in the United States, like you guys in Bangladesh, we want to make it locally because we have an emergency. So then we get several manufacturers making it. And we developed this device I will talk about, but even besides that, we were able to distribute helmets to many countries. So Bangladesh, Brazil, Canada, Kenya, and the United States. We distributed helmets, but also PEEP-Alert. We'll talk about that next. So PEEP-Alert is a monitoring of pressure and volume. So what I say is, if you are trying to give pressure to a person's lung, you better be careful, because you don't want to have them have to get a new lung. It's very delicate. And above basically 30 centimeters of water, the pressure of water, that's the PEEP. So if you bubble water through 30 centimeters, okay, 30 centimeters too much. 20, maybe the lung can say it's it. If you go, you can make it really high. So you have to be very careful about this. So this is why we start thinking about this. And this is an example of a study where we have a face mask. FM is a face mask. And you look at the face mask and the hospital mortality. Look at this. With the face mask, 50%. And with the helmet, only 27%. That's amazing. Big change. So we're really excited about these helmets when we see this data. And this was a study done at the University of Chicago with Arka Savakia, who was actually involved with that. She's a physician's assistant that went on to make helmet-based ventilation. And this money that I got actually supports her. So I support her and many of the helmet manufacturers and also people. So this money went a long ways. So this is a very exciting graph to me, to see this gigantic improvement, and the mortality continuing to be a difference over time. So gigantic difference. So we say, wow, this is great. So then we say, okay, now let's look at the rest of the literature. So many people worry there isn't good enough literature saying that helmet-based ventilation can be helpful. And quite frankly, why am I talking about it still, 2023? Because it is different procedure. People are so used to using ventilator, to have this big expensive machine next to a bed and doing it. But the trouble is, by the time that the person is that sick, the ventilator has all of these problems I talked about. The problem of the person having to be knocked out, to be quieted so that they don't fight it. Also, it's expensive, it takes a bed, and the helmet you can get early. Early is when you need it. For any of you that had COVID, you know it comes on very quickly. So we see the effectiveness of the parameters is better. The patient intubated or dead in 30 days. Without this, it was better. And we see with the face masks versus NIV, the helmet, you can see the results are much better on the right side here. Look at this, ulcerations 13% instead of 87%. Vocal cord 7% instead of 73%. This is a gigantic improvement. So it's really interesting when you see these data and you say, wow, big change. Then why don't people use it? And the doctors are scared. They're scared to do something new because, of course, they have people's lives they're worried about. And also they've been trained in something. So training is so central. This is the reason that helmet-based ventilation, well, here's some more literature. You can go to Oregon, this is the OFRR literature research. This is from this organization at Oregon State that John Selker and I and Frank Selker built. And there's a big literature about helmet-based and oxygen delivery. And then helmetbasedventilation.com. This is Arka Savakia's work. And she has done two things. Well, she's done many things. But one thing she did is she has tested almost all of the helmets. And also, did she get an oxygen to try it?
No, we can't.
If you want that, you can send her. So she tries these things and then she reports, she makes video of it. But also she has a great website that shows all of the ways people have tried to do positive pressure ventilation. She visits the manufacturers that makes these things, and she also talks to them about moving. But she gave a talk She gives talks at conferences about positive pressure respiration, and she also made a, oh, I talked about that next. I talked about her more later. She made a course to teach people, to train people. The OFRR, that's I talked about it already a little bit, but this man is at the University of British Columbia. He's a professor, and he's a professor that thinks about fluids and fluid dynamics. So we'll talk a little bit more about how he came into this story. And we work with all of these companies I already mentioned. Subsalve, they used to make things for decompression when you're diving. So when you're diving, then you come up, you have to bring up the pressure slowly. And they make lots of things for divers. So I call them up and I say, let's March 15th, I say, let's make some helmets. So they make helmets. And Omron, they make just a helmet for just areas, and we want to make pressurized helmets. So we got them to make them. And many others, which I don't need to talk about. But one of the problems we had is the helmets, many of the helmets, some of the ones that were being made, if you put them enough pressure on, they blow apart. Doctor goes crazy. Okay, you don't have a helmet that fails. So we, Frank Zelder and the rest of us, we made a kit for testing helmets. And then so now we can test them to see, do they leak? Do they break apart? So to make the industry reliable. So the best ones in the world are Dymar, Starman, Phoenix, Omron. But there's many things to consider. And there are other helmets that are made, and they all, after we made this kit to show them the problems, many of them went back and rebuilt, redesigned. So this is something we're very proud of. Not only did we make this kit and we sent it to the manufacturers to testing, but also we got a standards committee to get together to make a paper about what are the requirements for making a helmet for positive pressure ventilation that is reliable. And you can go to helmet-based ventilation and find out more about these things. So I'm very proud of those things. And then helmet-based ventilation, they made a training course. Working with Every Breath Counts, it's a consortium of people thinking about oxygen delivery all over the world. We got to talk to the World Health Organization. Before, they said mask or NIV or helmet, they are safe. They didn't look at literature. So then they heard us give our talk, and then we got together with them, and we got the World Health Organization to change their position on this. So very proud of that. But also, we give Arica, and I'm going to be supporting her. She's giving talks in New Zealand. Now she's going to give talks many other places. And we've gotten people to use the helmets many places. We got this, so OFRR also funded the PEEP-Alert, which I will talk about, but we also disseminated helmets to 15 hospitals in the United States, and also to especially University of Chicago, because University of Chicago, they are where a lot of the best research was done at the beginning, and they are using it all the time. They're actually using it in clinic. And Tufts Medical Center, they tried it, and but we sent 100 helmets to systems actually to Kenya, and oxygen generators and PEEP-Alerts, and then we got some feedback from them. That was another thing we did, but we've also sent some here, and the Oxyjet has been using PEEP-Alert, and that's why we're here. Very proud of you using it. Thank you very much. And I have to say, in our interactions, immediately the understanding of how to use it, what to do with it, why it's useful, and the very high quality engineering team, very impressed with working with you, always easy. I did not, see I stand back when I can, so I just let Morton and Mark do that. And the trouble is that all of this helmet and the PEEP-Alert still, we because getting to understand how to get dissemination, how to get people to use it and make it a standard procedure, this is difficult. Now, one of the people on here, we have Intersurgical, they make the StarMed helmet in Italy. Dymar is a good one in Italy. So one of the things I like about the Dymar is that you can open and get access to the patient. And also Haral, they're another one in Italy where you can get access to the patient. And Phoenix in India. Actually, I made my own helmet at the very beginning. I made one that I could, that anyone could make. And you probably didn't see this video. Maybe I'll play the video. But and then Sunrise is a distributor. I think one of the most important things, and you would probably think about this, is to work with a distributor that knows how to train and how to disseminate things. And Sunrise is fantastic. There's a woman named Ampreet who is there. Very, very, very impressive. In the Veterans Administration's hospital in Illinois, they actually were great because they have a cohesive team, and so they start using the helmet and they figure out how to use it, and they start using it all the time. Also, there's an NGO in Haiti that started using it and found the bubble helmet works very well, and they're disseminating it throughout the world. So it might be that we get you in touch with them too. Anyway, with that I go back to some of the things that happened in March. I started thinking about the fact that the mask is blowing COVID out into the room, and so I make this. Oops. Just a moment. So I make a 3D printed device that goes on this the ResMed mask, and I even sent it to ResMed. The ResMed is the company that makes these masks, and so this is what's fun about 3D printing. You know, with this one little device here, I can change a dangerous device that is blowing air, blowing COVID all over the room to be one that is completely safe. Okay, so I sent this to Harvard and to Tufts Medical Center, and then I also made this one. This one here, I didn't bring the 3M mask, but you can see this is a 3M mask, and again, this is the outlet, blowing out whatever's in you have, is blowing it out. The patient, right in front of you, is the patient, and you can make them sick. So I made this thing, and you snap it on the front, and now you have a safe helmet, just respirator, excuse me. So just kind of showing you some of the things. I like to make things, he said. Then I said, okay, what about making masks? So I made a mask, and the mask idea was to make it so you can talk easily through the mask, and also so people can see your face. And so I made all these masks. But what's really interesting about this mask, by the way, is you see this blue and clear tube. What is the reason for these tubes? Anybody? So what's nice about them is that behind me, I have the filter. Behind me, I have the exhale. So when I'm talking to you, all the air that is dangerous is behind me. It's not in front of me. I'm not taking air from you. I'm taking air from somewhere behind me. And this one here is like a Band-Aid. I made this one. I'm very proud of it. And you can see this is just very, very thin plastic, and it's that the wire holds it open so that it is able to get air in. And this one, the air opens it, and it becomes a valve, so only outlet. So anyway, I stopped making these because, well, we had more important things to do. We had to help people that were really sick. So, oh, here's video of me. I don't need to play it. Oh, there's another video of me. I don't need it to play. Let's go to the next one. So then I even made people start going into exercise place. So I make this bubble to go in front of you when you're exercising and to give you fresh air. But again, this is not life or death. Life or death is these helmets. And so this helmet here, here's my PEEP, which you probably laugh because it's reliable. I can get 20 centimeters of water. Before I had a PEEP valve, They're very inexpensive, but you cannot get them if you're not medical device. And so immediately in March 2020, I built some. Okay? And I built it in my shop. I used somebody's broken, see, I can fix this. There's a hacked CPAP. CPAP is just a blower that puts pressurized air. Surprisingly, you can get very high pressure from these CPAPs, high enough to actually be useful. We were getting up to 20 PEEP, 20 centimeters of water. Now this particular one, let me see if if it's worth playing. But here is I'm going to just build one right from nothing. I started with a Ziploc bag, and I just put some things on the Ziploc bag, and here I am wearing it 5 minutes later. So I'm going to, in this video, I'm talking about it. We don't have I will, but finally I make it. And back then there was really terrible problems. I mean, people were dying in the hallway at the hospital, and so making one that you can build. And what I really love about this one, let me see if I can go forward, is maybe I can go forward enough to show you that. So just a moment. So you see, I can pull it down, and I get access to the patient to clean out the sputum, to brush their teeth, to give them some food. I don't have to take off the helmet. Okay? And so this is what was special about it. Also, this tube is for giving them some liquid. I could have some liquid right now. So I made many different helmets, but then my brother said, maybe we're making these companies make the helmets, and we would do better off just helping these companies, and also there I am talking about it. And there's so many things going on that we don't have to do everything. We have to try to help people. So what we did is I also invested some money to help Arica make a training class, and you can do this online. Is to show doctor and also the medical staff how to do this treatment. Why I said over and over again is so important to make a training class is because the biggest problem that many of us have had is getting doctors to change their process at all. It's very difficult because they didn't have the equipment they needed, they had too many patients, they didn't know what to do, so we have to train them. And so Arica is a big hero. So what do you learn in your class? Early application. As soon as you need air, give them positive pressure. That's where we got those gigantic successes earlier. And that, but training the team so everybody is comfortable with it, super critical. And patient comfort is a necessity. So there's a recent JAMA article where they did a test with a helmet that was too difficult for the patients to take very long. They felt claustrophobic, he was saying, because it was too tight around their neck. And so they could only stand it for 4 to 5 hours. That wasn't enough. So that they got bad results out of the whole study. So it being comfortable, super critical. And you have to have enough pressure. If you don't have 5 PEEP or more, you actually aren't making this improvement that we're talking about. So you have to monitor the patient. That's where we got excited. Monitoring the patient. Nobody was monitoring patient without. Now, a ventilator, it has all these gauges, everything. Okay, it's monitoring. But it's monitoring the input. So we were thinking the output. What has happened to the patient? Not what are you giving to the patient. Because if the tube is clogged or something, maybe some sputum in it, we worry. So anyway, here's some of the manufacturers. They have on their sites for StarMed. They're the most famous one, Dymar. They have good access. Here's the Dymar one, that zipper around. That is like the zipper on top of mine. This one is around. So you can go to their websites, and they all have really good information. Dymar is good, and the Sunray, they distribute helmets, Dymar, and also Horel. And so if you're a hospital, you can go to them also. But I also thought, okay, so now I want to monitor the output. So here's some of my early approach. My early approach was use this flap inside a tube, just a vein, and I can tell how much is moving. So I had this monitor here, and I could measure, let me see, is this video? No. So anyway, I could monitor how much was going through. But that's only one measurement, just how much is going up. I want to measure pressure as well. So I try this one. This balloon, you see the balloon is, where's the balloon? The balloon is here. And then this one here, this black thing, this is a vein. So I calibrate this box, this green box, and now with, so inexpensive, you know, just a box with a piece of plastic in it, I can measure the volume, and with the balloon, the size of the balloon, I can measure the pressure. So now I'm mechanical, only something I can make for $1. Okay? It's great. Well, maybe the doctor wants something better. So we started thinking about a venturi. So this venturi, what happens is it is big, the air is going slow. It is thin, the air is going fast. So you have a sensor where it's going fast and where it's going slow. You measure the pressure differential, and you can measure the pressure and the volume. So how much is going through, also how much pressure. So we measure it, and Mark Johnson, he's a professor of fluid dynamics, also at the University of British Columbia. He makes this with his students in 2 days. So then we get measurements, and very exciting. And by the way, it's fun because when we're starting, he says, well, you have it with this vein. I said, this is not good enough. So I think it's always important to make better, better, better. You make one, but you don't settle for the first thing you make. You keep trying. And so we get this tremendous, this is the first day we try it. After, you know, one day design, 1 day manufacture, third day we try it. It's fantastic. And he says, okay, it's done. We open source it, everybody can make it. I said, I don't think so. We have to make some prototype. So then I convince Mark, this is Mark, right here, Professor Mark. And this is the beginning. Actually, it doesn't look like the beginning. This is actually the product over here of PEEP-Alert. But this is the very beginning. And at the beginning, we started off making a circuit board, 4-layer circuit board. These are the pressure sensors, and they are Honeywell pressure sensors. By the way, when we put these pressure sensors in place, the first ones, they were not good enough. So Honeywell, fancy manufacturer, we start measuring it, they were 5%, plus or minus 5%. Plus or minus 5% turns into gigantic error, and we cannot tolerate this. It's okay. And so then we eventually, this is we continue to 3D print the venturi. So that one is 3D printed with PET, PET. So this is the same material that is in your water bottle. So we printed this one. You can pass this around. And then we finally, in the end, these ones are printed by Hewlett-Packard, and you can see on them a picture of where the flow goes, which direction the flow goes. And also, you see a little thumbprint. Look at this thumbprint. That is so that you can take it off. The thumbprint is, put my thumb there, and I can take it off. So this is the final version. And if you want to, you can play with the user interface as it's traveling around. So, and then this one here is one of the first injection molds. So you can see that we very inexpensive to make an injection mold. Actually, only maybe a few $1,000s. So making the injection mold It's very, very inexpensive to be talking about. So the materials, there, keep playing. So the Venturi is 3D printed. The case is molded polycarbonate. The labels, 4 different iterations. We had to go to 2 different manufacturers to get those labels that were going to be reliable and sturdy and be able to be withstand. Also, the sensors. The first version we made 50 of these things, and we found out the sensors were no good. And of course, procurement during COVID, you know, it's difficult. So to get the right sensors, we had to wait 2 months. This held up our manufacturer. We were trying to get this thing out in 3-6 months. We did it in 12 months. I'm very proud of that because you'll see a little bit more. Not only that, but the processor. We made a whole version, all the firmware working, and then we decided, oh, we cannot make the sound and run the power supply and also make the lights and the display with this processor. We changed the whole processor, start all over. So this, you know, new circuit board, new firmware, everything. And then the annunciator. Oh my gosh, the annunciator. I designed, many times I spent just where do you put that noisemaker inside it to make this most sound? It's not easy. Audio is very complicated. And by the way, if we make another iteration, I know how to make that. That is now 75 decibels. To make it 100 decibels, we have to change something completely different. But that makes another injection mold. That makes another iteration of the manufacturer. I'm talking about these things because the process of making a product is an interesting process. And the batteries, for example, we started off with the batteries. The first place we go to batteries, $6 each. Okay? So this is $3 per battery. This is $6. $6 is a lot of money for US dollars. How much is that here? 11. And so we look. I found one for $1. Okay? So we replaced the batteries and we're able to do it. Why did we not use lithium ion? I love the lithium ion. High energy and density, lightweight, but we don't want fire. We want this to be, and why are we battery powered? We're battery powered for 100 hours. And and the reason we want it to be battery powered is that we don't have to have a wire. We don't have to, in the hospital, 100 hours, okay, that's 3 days, no problem. 3 days is good enough to be sure you're doing this correctly and all of that. And then, anyway, what's the most expensive piece of the whole equipment? It's not the Venturi, it's not the case, it's not the batteries, it's not the circuit board, it's the display. That stupid little display is the most expensive thing in that whole process. And still, our bill of materials is much more expensive than we want it to be. But we're proud of that, doing it. By the way, we made the circuit board. We started off making them in Canada, because the 3 of the people were in Canada when we started. One is now in Norway, but because of COVID, everyone moves around. Then we moved into China. And in China, we got higher reliability, quicker turnaround. So that was good. But all of these things, for example, you have to go through electromagnetic radiation testing. Okay, that was a very expensive process. That cost us almost $10,000. So very, very big expense in our budget. More expensive than making the injection mold was testing for electromagnetic radiation. And of course, it takes months. But the thing that's interesting, of course, is in the end, always they find something. So it was a ground that was loose, which means that you have the antenna kind of thing, and so there's problems with that. And then, calibration and reliability. We found a manufacturer, Logicam is the name of the manufacturer, is that it making this? No. Parts sharpened. Okay, birds are good. That's it. Making this thing reliably at the manufacturer, not easy. We had to make a whole jig to send to them for them to do the testing and to make sure that it is correct, because the first ones they made were not. And so this is what is required when you make a medical device, or any device actually. There's always quality control. And finally, getting what was wonderful about Logicam, they do the, they stuff the boards. That means they put the circuit board, the circuits on them. They test the electronics. They test the pressure sensors. They test the whole assembly. They put it in the box. They ship it for us. So many things. And, here is the circuit board. So this is the parts list. And the parts list in the end, it's more than $100. So then you have trouble because you have to sell this thing. Why would anybody pay $300 for a little device? Well, it takes a plastic bag and turns it into a medical device. This is a very important thing for training. It's also very important for safety. So here is the productization process. Maybe I gave you a lot of stories and steps about how am I doing for time? It's okay. But this is all of the things: the labeling, the manual, the packaging, the power supply. The power supply. Just designing the power supply to charge the battery. So many times going around because you don't want to. You want the battery to charge safely, right? By the way, the emergency authorization, FDA approval, this is EUA. So this is a little bit difficult usually. Going through FDA approval is supposed to take, people say it takes $5 million to make a medical company. We did this for much under $200,000. And EUA, during COVID, we send them, they call us up that night. Amazing. And then they give us, within a week, we have all of the lists of everything to change. We get back to them in 2 weeks. They get back to us in 1 week. We go back to them in 1 week. They come back to us in 1 week. So 3 rounds with them in less than a month, maybe a month and a half. But it's really incredible. Maybe that would take years. So during COVID, the whole world changed in the good ways. You see in this is our, from our website, you can see all of these things. You can also print a manual. You can also, but basically what you do is you have something like oxygen or CPAP, bringing in air and oxygen to this level. And then you have PEEP-Alert measuring how much pressure and volume came out. Then you have a filter to keep anybody from getting sick on the outside. Then you have a PEEP valve, this one, you set this to how much pressure you want. But actually, these PEEP valves, they cost so little money, they are not accurate. So this is another good thing, is that you can calibrate your PEEP valve with this PEEP-Alert. And so that was another piece that was very important. And so here's if you go to the PEEP-Alert.com, you will be able to see the manual. And this is the quick start guide, which is just 2 pages to show you everything you need to know, how to take off the venturi to clean it or replace it. We envision you use a new venturi for each patient. Maybe in Bangladesh, or maybe many places, people want to be a little more conservative and use it again. But that it was designed so we could replace the venturi for each patient. And here is us getting ready to do our emergency authorization, FDA approval. And we're actually using PEEP-Alert to measure another PEEP-Alert here. And I think many people, in fact, some of the manufacturers now are using PEEP-Alert as part of their manufacturing process to test their equipment. Because actually now, after all of these things I talked about, it is so, it has gotten, so return them when people it has become, they don't have good instruments. This instrument here that we use in the manufacturing process, this is $10,000. To get a really good pressure, you have a good one too. But this was an instrument grade device. So PEEP-Alert is kind of unique in being a simple thing. The competition is what is the name of that? There's a funny name. There's another thing. It's $700. So this is much better. So basically, and I need to get these back. These people, maybe they disassemble. But basically, the point is that it is very, very unusual to start a new industry. And what I didn't realize, and I think also you didn't realize when you're making Optigen, you're almost starting a new industry when you're making a new medical device of any sort, even if it's a small change. And we believe in it. As you see, there's good literature showing all of the ways it improves. There's some examples in Italy, and still the difficulty is getting adoption and working with people all over the world to try to get it used to save up to 30% of the lives that would be lost if you did not use this before the with that, I just want to open it up for questions. And thank you, PEEP-Alert, for coming, for showing us your equipment as well. So, any, let's see, did we get everything back?
One more.
There's one more. Okay, so it's an honest crowd. You can return things. But anybody have a question they want to ask?
Sir, any question?
Yeah. Aha, where's that one?
Sir, how did the PEEP-Alert recognize the flow?
The flow is...
The flow, the airflow, or any type of fluid flow, how did it recognize? What's the procedure for recognition of flow by PEEP-Alert?
Yes. So the PEEP-Alert, it measures the pressure difference between the air going fast in the thin part and going slow in the other part. So when it's going fast, it'll have a much higher pressure, and the difference between them, you can tell how much by the size of the hole. You can tell how fast it's going, as well as the pressure. So it's the differential.
So basically, I would like to know that how does it understand the difference of pressure inside the image?
Because it has two sensors. It has this sensor is for the, so there's two holes in the venturi, one at the thin part and one at the big part. And so by using a pressure sensor at each of them, I see the pressure when it's going through something this big, and the pressure when it's going through something that's that big. And that difference I can use to get both of those things. Does that make sense?
Yes, it is. Thank you.
Okay, it's interesting because I see everybody nodding. I think, oh, they understand. But you know, it's a little complicated, and I know it is. And that's what's fun about having. Really, this whole company was three people. It was Morton, who's a fantastic electrical engineer, firmware designer, very good designer. He and I wrote this whole book, all the drawings we did together. And then Mark Johnson, lots of experience with venturis and fluid flow, and then me, kind of a systems integrator and product designer with lots of various experiences.
Sir, another thing for interest that did you use the piezoelectric pressure sensor over your PEEP-Alert?
Yeah.
I'd like to know the pressure type of pressure sensor.
Yeah,
what type of pressure sensor?
The trouble with so there's many kinds of sensors, and piezoelectric sensors have they're dynamic. So the problem with piezoelectric is you can't get continuous high quality sensing with piezoelectric. AC, when you measure initial pressure, okay, but so. This one probably has a strain gauge in it, and it measures it by deflection. Okay, so there's lots of different kinds of sensors for anybody electrical engineering group here. There's ones with optical, you watch something move, or there's ones with resistive. You stretch it, almost anything. When you stretch it, the resistance changes. Almost any material. You can do it with capacitive. If two plates are different distance from each other, you can measure that, or you can do it with strain gauge. Strain gauge, very high quality thing. Oh, by the way, for the track point, this pointing device, here's the strain gauge. you can see, if you look carefully, the strain gauge is a long wire that is going in the direction you're measuring. So you can see that. And I just sent it around because, well, we're you've asked about sensors. This is strain gauge. And this one here is a ceramic strain gauge. And it's just a piece of ceramic that stretches. Almost anything when you stretch it, it changes resistance. So piezo-resistant, they call it. So anyway, I don't need to, I guess. So those are the kinds of sensors. I don't know, maybe electronic sensors is unnecessary, but it's fun. Any other questions? Yes?
Sir, for calibration? For calibration purpose, which gas type did you use? Did you use oxygen gas or normal airflow for PEEP-Alert? For the calibration.
PEEP-Alert. Okay, so there's so many ways of using PEEP-Alert. You can use it with the house air. So most hospitals they have on the wall they have oxygen and they have CO2 and they have air pressurized. Okay, you can just use that. And it's great with a flow meter and a PEEP and you put on your bubble helmet. Okay, or you can use it with CPAP. CPAP is a fan and it blows, and then they have a computer to control it. And many people with sleep apnea will wear a mask at night. But these things are surprisingly good, and in fact they are better in many ways because they regulate the pressure. And then, or you can use a BiPAP, or you can use a ventilator. Some people even run this with a ventilator. When you have a ventilator, of course, it has its own monitoring on it. But so there are many ways to drive these things. The preferred way, after 3 years of playing with these things, is a CPAP. And what's wonderful about a CPAP machine, that there are, maybe in America, there are millions and millions of people using them every day. And the price of a CPAP machine is about the same price as the PEEP-Alert. And so it's a really great way to deliver it. Now, the problem with the CPAP is you have to bring in only air, it's not good enough. So you have to have an inlet into the CPAP machine for oxygen. I'm not sure, am I answering your question? You asked a different question?
Yeah.
Okay, because maybe I didn't hear.
Basically, my question was, if we use different types of gas flow, so the flow rate and maybe gonna change. So how you are dealing with that issue? Basically, if we measure the flow rate of an oxygen gas, if the flow rate showing that 50 or 60 liter, if we deliver airflow, that's gonna be different. So that's the issue actually.
Because of the density of different gas.
I would like to. So the mass flow rate remains same. The mass flow rate remains same, but due to the difference of the density of gases, the flow rate of gas.
Push the button and wait.
Yeah. I think I'm audible.
Okay. All right.
Yeah.
So you're saying that the different density is not so
Yeah,
big?
due to difference of the density, the flow rate is dependent on the type of gas. Like for air, the density is low, and for oxygen, the density is higher. So during when the PEEP-Alert is computing the flow rate, so is it considering the density of air or
No, it is assuming.
How the calibration
It is
done?
assuming you mixed it correctly. Okay, because we do not have you know.
The FI is yeah.
I get it. So the question is, we wanted to put in a CO2 sensor. We wanted to put in to be able to measure your. I understand. We when we were considering what to make this product, we thought, okay, we could make it very fancy. We put in a carbon dioxide sensor. We put in an oxygen sensor. We measure exactly what is going on, and then we start realizing already it's expensive. And then we start saying, okay, is this good enough? Well, if we have the setup correct, then the density is going to be constant with. Okay. So if the density is going to be from a correct oxygen flow, and then we are good enough. But yes, it is not perfect. In fact, when on our first iteration, many times we made the, we would record your breathing, and we start having measuring whether you're breathing too fast, you know, or breathing too slow, and then we realize, oh, to get this through approval, if we start trying to say we're doing diagnosis, then the approval will not happen and will happen in 3 years. So we really wanted to simplify the system as much as possible. It is not a complete, it is not every instrument is only good enough for a purpose.
So yeah, I have another question. I have a follow-up question. So yeah, I was going to ask if you are planning to integrate a FIO sensor in your device, and that would make the device.
Do they include what in it?
FIO sensor. Oxygen percentage.
Yeah, I mean that's another. So you know, so right now what our goal is to get people to be able to measure pressure and volume. That's it. And of course, if it is accepted, then we start measuring FiO2, we start measuring breathing respiratory rate, we start measuring CO2. It becomes diagnosis device, and we have to be careful, and also we have to just get this to product in 1 year. We had so many challenges that we just say, okay, we get good quality pressure sensors. That was hard enough. Okay, so then, yeah, so that's where we stop as far as
So are you planning to integrate it in future?
it's hard to plan the future. Yeah. So what are we going to do next, you ask? And what we are doing right now, the most important thing is not developing better and better. The most important thing is to get people to use it and to change their procedures and to save people's lives. Then of course, if we have requests, my number one thing is a louder alarm. More louder. That is if you want to know what my next goal would be, is to make it louder. And before, at the very beginning, we were going to work with some people in Kenya, the engineers. And they want to say, oh, we will connect them all, and we'll have it in a network, we'll get to the nurse's station. Okay, we have wireless. Okay, that's not that hard. It's just a whole engineering project. And to get this, just to get through, I'm very proud of choosing the simplest one. That is what we really try to do. So it's not that we don't have many ideas of better ones to make. And I think that's what's really interesting as a product designer, is what is the simplest thing you can make that's going to be useful and is going to save people's lives, or to whatever problem you want to solve. That is where you have to do. Because once you start saying, oh, I can make everything, you start taking more and more time, and everything interacts, and it becomes more and more complicated, and you don't complete your job. And the price of making this product, maybe nobody believed that this could be made in 1 year for under $200,000 as all the way through approval. Nobody. But we did it. So I'm proud of that. But what I'm not proud of is that it isn't being used in 100,000 doctor hospitals.
Thank you. You did a great job.
Okay, well maybe. Did you have a question?
Yeah, maybe last question. So, I just see your story, and we've also gone through different challenges, and
Yes.
So I feel like some of the things are the challenges we face is because of our geographic location. That's some kind of disadvantage.
People like to whine about their. You say it's your geographical. It's a beautiful place you are.
Yeah, no, I'm not saying like.
Bananas grow on the trees in the driveway. It's a great place.
Okay, maybe I'll rephrase it. Like to give some concrete examples, like when we go for regulatory approvals, we face different kind of challenges. Like because let's say the approving authority, there's no person actually who understands technology. So that's kind of some of the challenges we face. So I'm asking you like for your advice in a sense, like is someone trying to innovate, important projects in let's say in a developing country like Bangladesh?
First of all, I think that
What do you think?
do not keep saying this.
Yeah.
Okay. This is a problem. Trying to develop technology anywhere has all of these problems. So I have had terrible problems communicating why something is useful all my career. This device took me 8 years to get it accepted into IBM. So many stories. I can tell you 100 stories of everything was wrong. So for example, even the rubber top that you put your finger on for a pointing device, they want to make it slippery. Okay? The company, after I'd already designed it, they said, oh, we don't know how to make it sticky. So many mistakes are made. And when we were making this ready for trying to get approval, we had to explain everything to the approval people. They didn't understand what we were talking about. Like I said, World Health Organization didn't understand. Okay? If they don't understand, nobody understands. So you start off by saying, well, I'm going to explain this to somebody who is smart but not educated. That is always the case, because everything we make that is new is something that people haven't seen before. And if they haven't seen it before, you start at the beginning and you make it so easy, step by step by step, that they cannot give you trouble. So when we did it, we had measured, we knew exactly what the cleaning process was. We had tested the cleaning. We tested the temperature. We dropped it from 3 feet. We all of these things. We had. So one example of a problem. Okay, this contained environment. We found out that it started corroding inside because the gas from the charging battery. So we changed the battery. But you see, I have a lot of experience with these. Where did my pointing devices go? The sensors. So just to give you an example, those sensors. One time, when the manufacturer, they put too much sulfur in the rubber, and the rubber top that goes on top, the red rubber top, the sulfur, it starts getting in the air near the sensor, and the piezo-resistive sensor, it starts corroding, and then it stops working. Okay, so everything goes wrong. So even if they said, oh, I know everything about it, nobody knows everything about a new product. So it doesn't matter what country you're in. You have to teach people as though they know nothing, and you treat them like you have to be respectful, but then also expect them not to understand, and then slowly teach them step by step. I don't know if that's an answer, but that's my experience.
Thank you very much.
Thanks for coming. And actually, it is almost the end of the semester, and all of you have, many of you joined here, and you are doing many interesting projects, and I hope you have done many things. And I would like to thank you very much for taking our time, and you can see all the noises. So it looks like promising. There looks like many things can happen. You can see the noise.
Oh, so much is going. So happened. I don't know about the noise, but I saw the laboratory. That's more interesting. Oh, yeah, the laboratory is interesting because everybody's making something, and they're trying things out, and they are working together as teams, and so that's impressive. So I think sometimes the question was it whether you can do more by yourself or as a team, and it's a complicated balance. I want everybody to think, what can I do by myself also? But it's a nice laboratory. And
so in our department we have both of the modalities. So we have like individual projects, and of course we need the teams as well.
yeah.
So in the third year we do many projects, caption projects.
Do you have a machine shop also, or just these
Machine shop there is central machine shop. So,
central?
yeah.
Yeah, that means that you don't get to use it.
So when I was in mechanical engineering, so we go there. But when we were staying here, in biomedical engineering, we have very limited resource on that machine shop thing.
Maybe you can help them go to the central and learn how to use mechanical.
No, this is open to all.
So then it's great.
That machine shop is actually that's a big shop and workshop, and it would be difficult for individual department to maintain that, afford that, and so So we just have it in central.
Okay. Well, a lot of universities, when they say central, that means the technician will not let you touch the machine. So I'm teasing him because I want every student to go to this central place and spend 3 weeks learning how to use this equipment, because if you use this equipment, then the way you design things is different, right? Because if you really have your hands in it, and then you have the theory, then the two go together. If you just have the theory, maybe you never get a real understanding. I don't know if you agree.
No, it's absolutely right. So yeah, I think we can end here. So thank you for your for joining here, and as there are third year students, today our lab will be open until 8 p.m. so you can work. Okay, thank you.